the heart of the Milky Way. Think about the Milky Way for a moment. That band of light stretching across dark skies, billions of stars, arranged in a great spiral, arms reaching outward, dust lanes weaving between them, and at the very center, hidden from view, lies the heart, the core that holds everything together. For most of human history, we didn't know what lay at the center of our galaxy. We couldn't see it. Too much dust, too much gas blocking the view. The galactic center is obscured in visible light, hidden behind layers of cosmic debris. But the heart is there, beating with invisible energy, anchoring the spiral arms, holding our solar system in its orbit as we circle the galaxy once every 230 million years. The heart of the Milky Way isn't a star. It's not a cluster of stars. It's something stranger, something that bends space and time, something that challenges our understanding of physics. It's a black hole, a supermassive one, and its name is Sagittarius A, the hidden center of our galaxy. The center of the Milky Way lies in the direction of the constellation Sagittarius, 26,000 light-years away. That's the distance light travels in 26,000 years, an incomprehensible span. The center is hidden from us, not by distance alone, but by material. Clouds of dust and gas fill the galactic plane, blocking visible light from reaching Earth. If you point a regular telescope toward Sagittarius, you see stars, nebulae, but you don't see the center. It's invisible. However, dust and gas are transparent to certain wavelengths. Radio waves pass through. Infrared light penetrates. X-rays reveal the energetic processes at work. Using these wavelengths, astronomers can peer through the obscuring material and see what lies beyond. What they found was unexpected. A compact region of intense radio emission, a point source, small yet incredibly luminous in radio frequencies, and around it, stars moving at extraordinary speeds, orbiting something invisible, something massive. The hidden center of our galaxy became visible through other eyes, through radio telescopes and infrared detectors, and what they revealed changed everything. The mystery behind the clouds of dust. The galactic center is shrouded in dust. Not the dust you find in your home. This is cosmic dust, tiny grains of carbon and silicate, scattered throughout interstellar space. Each grain is microscopic, but there are trillions upon trillions of them. Together, they form clouds that block visible light. The dust absorbs short wavelengths, like blue and green light. It scatters them. And what's left is mostly red light, and even that gets dimmed. By the time light from the galactic center would reach us, it's been absorbed and scattered so many times that virtually nothing gets through. This obscuration frustrated astronomers for decades. They knew there was something at the center. They could see the structure of the galaxy, the way stars orbited, but they couldn't see the heart directly. The mystery behind the clouds of dust was both a challenge and a clue. It told astronomers they needed different tools, different wavelengths, and so they turned to radio astronomy, infrared observations, and X-ray telescopes, technologies that could see through the veil. And slowly the mystery began to unravel. The radio source that shouldn't exist. In 1974, astronomers detected something unusual, a strong radio source at the galactic center, compact, bright, and unlike anything they'd seen before. They called it Sagittarius A, after its location in the constellation. Later, the brightest component was designated Sagittarius A, pronounced Sagittarius A star, the asterisk denoting something special. The radio source was peculiar. It was small, far smaller than expected for something so luminous, and it was stable, emitting radio waves consistently over time. At first, no one knew what it was. A dense cluster of stars? A pulsar? Something else entirely? The radio source that shouldn't exist puzzled scientists for years. Its properties didn't match known objects. It was too compact to be a star cluster, too stable to be a transient event, and its radio emission suggested something fundamental was happening, something involving magnetic fields and accelerated particles. The discovery of Sagittarius A was the first hint that something extraordinary lay at the heart of the Milky Way, something that would take decades to understand. The discovery of Sagittarius A. The formal discovery of Sagittarius A** came in the mid-1970s. Radio astronomers, using the Very Large Array in New Mexico, detected the compact radio source at the galactic center. It was bright, persistent, and occupying a tiny region of space. The coordinates were precise. The emission was undeniable. But what was it? The name Sagittarius A** was coined to distinguish this compact source from the larger, more diffuse Sagittarius A complex surrounding it. The asterisk was chosen because in atomic physics, excited states are marked with an asterisk, and this object was certainly exciting. The discovery was significant, but not immediately understood. It took years of follow-up observations to piece together the picture. Radio observations revealed the source's size and brightness. Infrared observations showed stars orbiting nearby. X-ray telescopes detected flares and hot gas. Slowly, the evidence accumulated, and a startling conclusion emerged. Sagittarius A** wasn't a star. It wasn't a cluster. It was a black hole, a supermassive one. The discovery of Sagittarius A** marked the beginning of a new chapter in galactic astronomy. The astronomers who found a signal in 1974. In 1974, Bruce Ballack and Robert Brown were using radio telescopes to study the galactic center. They were mapping radio emissions, trying to understand the structure of the Milky Way's core, and they found something, a compact, bright radio source that stood out from everything around it. The signal was clear, strong, persistent. It didn't flicker or fade. It was there, day after day, week after week. Ballack and Brown knew they'd found something important, but they didn't immediately understand what. The technology of the time limited how much detail they could see, but the signal was unmistakable. Over the following years, other astronomers joined the effort. They used more powerful telescopes. They observed at different wavelengths, and they refined the measurements. The signal became clearer, more defined, and the conclusion became inescapable. The astronomers who found a signal in 1974 opened a door. They gave us the first glimpse of the black hole at the center of our galaxy, and they set the stage for decades of research that would culminate in a photograph of the unphotographable. The strange point of light at galactic core. At the heart of the Milky Way, there's a point. Not a star, though it's surrounded by stars. Not a nebula, though gas swirls around it. It's a point of concentrated gravity, so intense that it warps the fabric of space and time. In radio wavelengths, it appears as a bright spot. In infrared, it's often quiet, occasionally flaring. In X-rays, it bursts with energy now and then. But in visible light, it's invisible, hidden. The strange point of light at galactic core is Sagittarius A**, and it's strange because it shouldn't emit light at all. Black holes trap light. They don't let it escape, but the material around a black hole, the accretion disk of gas and dust spiraling inward, heats up. It glows, and as that material approaches the event horizon, it emits radiation across the spectrum. What we see isn't the black hole itself, it's the environment around it, the heated gas, the accelerated particles, the twisted magnetic fields. The strange point of light is a shadow, a silhouette, the absence of light surrounded by brilliance. The name that became legendary, Sagittarius A, 3 syllables, and an asterisk. It's not the catchiest name, but it's become one of the most famous designations in astronomy. The name comes from its location, Sagittarius, the constellation where it lies, A for the radio source, Sagittarius A, and the asterisk, marking it as the special compact component. Over the decades, Sagittarius A has become synonymous with the black hole at the center of our galaxy. It's appeared in textbooks, documentaries, and scientific papers. It's been the subject of Nobel Prize-winning research, and it's been photographed, its shadow captured by a global network of telescopes. The name that became legendary is a reminder of how scientific nomenclature works. Not always elegant, not always poetic, but functional, and in this case, memorable. When you hear Sagittarius A asterisk, you know exactly what it means. The heart of the Milky Way, the supermassive black hole that holds our galaxy together. A name that represents one of the most profound discoveries in modern astronomy. The star cluster orbiting the unknown. Near Sagittarius A asterisk, there's a cluster of stars, dozens of them, packed tightly around the galactic center. They're called the S stars, a designation that simply means they're in the vicinity of the radio source. These stars are unusual. They're bright, hot, and young, and they're orbiting something invisible. For years, astronomers tracked these stars. They measured their positions, their velocities, their orbits, and what they found was astonishing. The stars were moving fast, incredibly fast. Some were traveling at thousands of kilometers per second. Their orbits were elliptical, swooping close to a central point, then swinging out again. The star cluster orbiting the unknown provided crucial evidence. The stars' motions were dictated by gravity, and the gravity required to move them so quickly had to come from an enormous mass, concentrated in a tiny region. The mass was there, invisible but undeniable, and the only thing that could fit the observations was a supermassive black hole. The S stars became cosmic test particles, revealing the presence of something we couldn't see directly, the evidence of an invisible mass. The S stars orbit a point, not a star, not anything visible, a point in space where nothing glows, but their orbits are precise, elliptical, following Kepler's laws, and those laws depend on mass. By measuring the orbits, astronomers could calculate the mass at the center. It was straightforward physics. Observe the motion, measure the speed and distance, apply Newton's or Einstein's equations, and solve for mass. What they found was staggering. The mass was roughly 4 million times that of the Sun, and it was contained in a region smaller than the orbit of Mercury. No cluster of stars could be that dense. No normal object could exist in such a compact form without collapsing. The evidence of an invisible mass was overwhelming. There was something at the center of the galaxy, something with the mass of millions of suns, something invisible, and the only explanation that fit was a black hole, a supermassive one. The evidence was indirect, but it was ironclad. The stars moving at impossible speeds. The S stars don't just move, they race. One star, called S2 or S02, depending on the catalog, reaches speeds of over 7,600 kilometers per second at its closest approach. That's about 2.5% the speed of light. For a star, that's unimaginable. Our sun orbits the galaxy at about 220 kilometers per second. S2 is more than 30 times faster, and it's not the only one. Other S stars also move at extreme velocities. The stars moving at impossible speeds are proof of the black hole's gravity. To accelerate a star to such velocities requires an enormous gravitational field, and to keep it in orbit requires a precise balance between speed and gravity. The observations of these stars are delicate. Astronomers use adaptive optics to correct for atmospheric distortion. They track the stars' positions over years, even decades, and they watch as the stars trace their orbits, confirming again and again that something massive and invisible sits at the center. The stars' speeds aren't just impressive, they're a window into the fundamental nature of gravity. The gravity that bends space and time. Einstein taught us that gravity isn't a force in the traditional sense. It's a curvature of space-time. Mass bends the fabric of the universe, and objects follow the curves. Near a massive object, Space-time is warped. Clocks run slower. Distances stretch. Light bends. And near a black hole, these effects become extreme. At the event horizon of Sagittarius A, time nearly stops. From our perspective, an object falling toward the black hole would appear to slow down, freeze, and fade. Light from that object would be redshifted, stretched to longer wavelengths. The gravity that bends space and time is one of the most profound aspects of black holes. It's not just that they trap light, it's that they fundamentally alter the nature of reality in their vicinity. Einstein's general relativity predicted these effects, and observations of Sagittarius A confirm them. The orbits of the S stars show relativistic effects, precession, time dilation, light bending, all exactly as Einstein predicted. The black hole at the center of our galaxy is a laboratory for testing our understanding of the universe. The search for the Milky Way's black hole. For decades, astronomers suspected there was a black hole at the center of the Milky Way, but suspicion isn't proof. They needed evidence, concrete measurements, observations that could rule out all other explanations. The search began in earnest in the 1990s. Two teams, one led by Andrea Ghez at UCLA and the other by Reinhard Genzel at the Max Planck Institute, embarked on ambitious programs. They would track the stars near the galactic center, measure their positions with extraordinary precision, and watch their orbits over years. It was painstaking work. The observations required the best telescopes, the most advanced adaptive optics, and decades of dedication. But slowly the picture emerged. The stars were orbiting a point, an invisible point, with a mass of millions of suns. The search for the Milky Way's black hole culminated in proof, undeniable, reproducible proof. And in 2020, Ghez and Genzel were awarded the Nobel Prize in Physics for their discovery. They had found the heart of the galaxy. The work of Andrea Ghez and Reinhard Genzel. Andrea Ghez and Reinhard Genzel dedicated their careers to studying the galactic center. For more than 2 decades, they observed, they measured, they analyzed. Year after year, they tracked the S stars, watching them move, plotting their orbits, refining their measurements. It was a marathon, not a sprint. Gez's team used the Keck Observatory in Hawaii. Genzel's team used the Very Large Telescope in Chile. Both teams pushed the limits of technology, developing new techniques to see through the Earth's turbulent atmosphere. They used adaptive optics, systems that correct for atmospheric distortion in real time. They used infrared cameras, which could see through the dust, and they used astrometry, the precise measurement of stellar positions. The work of Andrea Ghez and Reinhard Genzel was collaborative, yet also competitive. Both teams were racing to prove the existence of the black hole, and both succeeded. Their results agreed. The black hole was there, and it was massive. Their discovery was one of the great achievements of observational astronomy, a testament to patience, precision, and perseverance. The decades of observation that proved it. Proof takes time. You can't just observe a star once and claim you've found a black hole. You need to watch it move, map its orbit, confirm that it's following the path predicted by gravity. From the early 1990s through the 2010s, Ghez and Genzel's teams observed the galactic center. They took images every few months, sometimes more often. They tracked dozens of stars, but one star in particular, SES 2, became the key. SES 2 has an orbit that brings it very close to Sagittarius A. It completes one orbit every 16 years. In the late 1990s and early 2000s, SES 2 was approaching its closest point, and in 2002, it whipped around the black hole at incredible speed. The observations of that periapsis, the closest approach, were crucial. They confirmed the mass, they confirmed the compactness, and they ruled out alternative explanations. The decades of observation that proved it were not glamorous. They were repetitive, meticulous, and demanding, but they provided ironclad evidence. Sagittarius A is real, and it's a black hole, the Nobel Prize for the center of everything. In 2020, the Nobel Prize in Physics was awarded for black hole research. Half went to Roger Penrose for theoretical work on black holes. The other half was shared by Andrea Ghez and Reinhard Genzel for their discovery of the supermassive black hole at the center of the Milky Way. It was a moment of recognition, not just for Ghez and Genzel, but for their teams, for the decades of work, for the technological innovations, and for the sheer persistence required to prove something that couldn't be seen directly. The Nobel Prize for the center of everything was about more than a single discovery. It was about understanding our place in the cosmos, about proving that galaxies have hearts, that those hearts are black holes, and that we can study them, measure them, and understand them. The prize was a celebration of human curiosity, of the drive to explore the universe, and of the fact that even the most hidden secrets can be revealed with time, technology, and determination. The star known as CES 2, a cosmic test particle. CEN 2 is a star, a bright blue star, about 15 times the mass of the Sun. It's young, only a few million years old, and it orbits Sagittarius A asterisk in a tight ellipse. CEN 2's orbit is special. Its periapsis, the closest point, brings it within about 120 astronomical units of the black hole. That's roughly the distance from the Sun to Pluto, but in the context of the galaxy, it's incredibly close. At periapsis, CEP 2 is moving at about 2.5% the speed of light, and it's experiencing intense gravitational effects, time dilation, gravitational redshift, orbital precession. The star known as CEP 2 is a cosmic test particle. Astronomers use it to test Einstein's general relativity, to measure the mass of the black hole, and to probe the environment around Sagittarius A asterisk. Every orbit of CEP 2 provides new data, new opportunities to confirm or challenge our understanding of gravity. CEP 2 is just one star among billions, but it's one of the most important stars we've ever observed. The 16-year orbit that revealed the truth. SELS 2 takes about 16 years to complete one orbit around Sagittarius A. From 1992, when observations began, astronomers have watched it complete more than one full orbit, and with each orbit, the evidence for the black hole becomes stronger. The orbit is elliptical, highly eccentric. At its farthest point, SELS 2 is about 1,900 astronomical units from the black hole. At its closest, only about 120. The change in distance is dramatic, and so is the change in velocity. The 16-year orbit that revealed the truth was carefully documented. Every few months, astronomers measured S2's position, they plotted its path, and they compared the observations to theoretical predictions. The match was perfect. SELS 2 was following the orbit predicted by general relativity. The precession of its orbit, the way the ellipse rotates over time, matched Einstein's equations, and the gravitational redshift of light from S2, measured during its close approach, confirmed the intense gravity near the black hole. SELS 2's orbit was the smoking gun, the undeniable proof that Sagittarius A is a supermassive black hole. The calculation of 4 million solar masses. By observing C2 and other stars, astronomers could calculate the mass of Sagittarius A. The math is straightforward. You measure the star's velocity and distance. You apply Kepler's third law, or more precisely, Einstein's equations, and you solve for the mass. The result is about 4 million times the mass of the Sun. More precisely, about 4.15 million solar masses, with some uncertainty. That's an enormous mass, but it's compressed into a tiny region. The calculation of 4 million solar masses is what defines Sagittarius A as a supermassive black hole. It's not the biggest black hole we know. Some reach billions of solar masses, but it's massive enough to hold our galaxy together. The mass calculation is remarkably precise. Thanks to decades of observations, we know the mass to within a few percent, and that precision allows us to probe other aspects of the black hole: its size, its event horizon, and the environment around it. 4 million suns compressed into darkness. It's a number that's difficult to comprehend, but it's real. The size of a point smaller than our solar system. 4 million solar masses is a lot of mass, but the region containing it is incredibly small. The event horizon of Sagittarius A, the boundary beyond which nothing can escape, has a radius of about 12 million kilometers. That's roughly the distance from the Sun to just inside Mercury's orbit. In cosmic terms, it's tiny. For comparison, the Milky Way is about 100,000 light-years across. Sagittarius A occupies a region that's about 0.000001 light-years. It's a point, essentially, a dimensionless location where 4 million suns worth of mass has collapsed into infinite density. The size of a point smaller than our solar system is what makes Sagittarius A* so extraordinary. All that mass, all that gravity, concentrated in such a small space. It's a testament to the extreme nature of black holes, and it's why observing Sagittarius A* is so challenging. The black hole itself is tiny. Even with the best telescopes, resolving its event horizon requires unprecedented precision. But that's exactly what astronomers achieved in 2022. The definition of a supermassive black hole. Black holes come in different sizes. Stellar mass black holes, formed from collapsing stars, have masses of a few to a few dozen suns. Intermediate mass black holes, if they exist, might have hundreds or thousands of solar masses. And then there are supermassive black holes. These giants have masses from hundreds of thousands to billions of suns, and they reside at the centers of galaxies. The definition of a supermassive black hole is somewhat arbitrary. Generally, anything above about 100,000 solar masses qualifies. Sagittarius A, at 4 million solar masses, is comfortably in that category. Supermassive black holes are different from their smaller cousins. They don't form from collapsing stars. They grow over time, accreting matter, merging with other black holes, and slowly building up mass. They're thought to play a crucial role in galaxy formation and evolution. Their gravity shapes the distribution of stars and gas, and their energy output, when they're actively feeding, can influence the entire galaxy. Sagittarius A is our closest example of a supermassive black hole, and studying it helps us understand these cosmic giants throughout the universe. The event horizon, hidden in darkness. The event horizon is the defining feature of a black hole. It's the boundary, the point of no return. Once something crosses the event horizon, it can never escape. Not matter, not light, not information. At Sagittarius A*, the event horizon is about 12 million kilometers from the singularity at the center. But the event horizon isn't a physical surface. It's a mathematical boundary, a place where the escape velocity equals the speed of light. Outside the event horizon, escape is possible, at least in theory. Inside, it's not. The event horizon hidden in darkness is, ironically, the only thing we can see about a black hole. We can't observe the singularity. We can't probe the interior, but we can see the event horizon's silhouette, the shadow it casts against the light of the surrounding accretion disk. That shadow was photographed in 2022. It's not the event horizon itself, it's the region just around it, where light is bent so strongly that it creates a dark circle, but it's as close as we'll ever get to seeing a black hole directly. The region from which nothing escapes. Inside the event horizon, physics changes. Escape becomes impossible, not because there's a barrier, but because space-time is so curved that all paths lead inward. Imagine trying to climb out of a hole where the walls are vertical. No matter which direction you move, you're always going down. That's what it's like inside a black hole. Every direction, even up, leads toward the singularity. The region from which nothing escapes is absolute. It's not a technological limitation. It's not something we might overcome with better rockets or more energy. It's a fundamental property of space-time. Once inside, you're done. You're headed toward the singularity, and there's nothing you can do about it. This region has fascinated physicists for decades. What happens inside? Does space become time-like? We don't know. General relativity provides equations, but they break down at the singularity, and quantum mechanics might have something to say. But we don't have a complete theory of quantum gravity. The region from which nothing escapes is the ultimate mystery, the light that curves around its edge. Near a black hole, light doesn't travel in straight lines. Gravity bends its path, and near the event horizon, the bending is extreme. Some light is captured, pulled into the black hole, but some light skims the edge, bent into a circular orbit. This is called the photon sphere, light orbiting the black hole in a precarious balance. Most of this light eventually falls in or escapes, but for a moment it circles. The light that curves around its edge creates the shadow we see in images of black holes. The shadow is actually about 2.6 times larger than the event horizon. It's caused by gravitational lensing. Light from behind the black hole is bent around it, creating a bright ring, and in the center, where light can't escape, there's darkness. This bending of light is one of the predictions of general relativity, and observing it confirms Einstein's theory. The light curves exactly as predicted, creating the distinctive shape we see in photographs of Sagittarius A asterisk, a bright ring, a dark center, the signature of a black hole, the gravity that stops time itself. One of the strangest predictions of general relativity is time dilation. Near a massive object, time runs slower. The effect is small on Earth, but near a black hole, it becomes extreme. At the event horizon of Sagittarius A asterisk, time effectively stops. From our perspective, an object falling toward the black hole would slow down as it approached the horizon. It would appear to freeze. Its light would redshift, becoming dimmer and redder, and eventually it would fade from view, seemingly frozen at the edge. But from the perspective of the falling object, nothing unusual happens. Time passes normally. The object crosses the horizon and continues toward the singularity. There's no moment where it feels time stop. The gravity that stops time itself is one of the most mind-bending aspects of black holes. It shows us that time is not absolute, it's relative. It depends on where you are and how fast you're moving. Near a black hole, time becomes plastic, stretched by gravity into something almost unrecognizable. The core that holds our galaxy together, Sagittarius A asterisk, isn't just an interesting object. It's the anchor of the Milky Way. Its gravity holds the galaxy together, not directly in the sense that it pulls on every star, but in the sense that it defines the center, the galactic nucleus. The dense concentration of stars near the core orbits Sagittarius A. Those stars, in turn, influence the orbits of stars farther out, and so on, in a cascade of gravitational interactions. The core that holds our galaxy together is surprisingly small for such an important role. The mass of Sagittarius A is only about 0.001% of the total mass of the Milky Way. Most of the galaxy's mass is in stars, gas, and dark matter, but the black hole defines the center. It's the point around which everything else revolves. Without Sagittarius A asterisk, the galaxy would still exist, but it would be different, less organized, less structured. The black hole isn't just a curiosity, it's a fundamental part of the galaxy's architecture, and understanding it helps us understand how galaxies form and evolve. The role of Sagittarius A in galactic stability. Supermassive black holes are thought to play a key role in galaxy evolution. They regulate star formation, they heat gas, and they inject energy into their surroundings. Sagittarius A asterisk is relatively quiet now, but it wasn't always. Evidence suggests it was more active in the past, feeding on gas and emitting powerful radiation. That radiation would have heated the surrounding gas, preventing it from collapsing and forming stars. This feedback mechanism helps regulate galaxy growth. Without it, galaxies might form stars too quickly, exhausting their gas supplies. The role of Sagittarius A asterisk in galactic stability is subtle. It's not directly holding stars in orbit, but it's influencing the environment, shaping the distribution of gas, and indirectly affecting star formation throughout the galaxy. Studying Sagittarius A asterisk helps us understand this feedback, how black holes and galaxies co-evolve, and why galaxies look the way they do. The black hole at the center isn't just a passenger, it's a driver of galactic evolution. The disk of stars that circle in silence. Near Sagittarius A asterisk, there's a disk of stars, not an accretion disk, a disk of actual stars, orbiting the black hole. These stars are young, massive, and hot, and they're arranged in a flattened structure. The disk of stars that circle in silence is a puzzle. How did these stars form so close to the black hole? Normally, the intense gravity and tidal forces near a black hole would disrupt star formation, yet here they are. One theory is that they formed farther out and then migrated inward. Another is that they formed from a massive disk of gas that somehow survived near the black hole. The truth is, we're not sure. The stars orbit in near silence. There's no sound in space, of course, but there's also no visible drama. They don't collide, they don't explode, they just orbit, tracing their elliptical paths around the invisible mass at the center. The disk of stars is a reminder that even in the most extreme environments, the universe finds ways to create and organize, and that there's still much we don't understand. The formation of the Milky Way's center. How did Sagittarius A asterisk form? The answer is lost in time. The Milky Way is about 13 billion years old. Sagittarius A asterisk is likely almost as old, but we don't know exactly how it came to be. One possibility is that it formed from the direct collapse of a massive gas cloud in the early universe. Another is that it grew from smaller seed black holes that merged over time, or perhaps it formed from the first generation of massive stars, which collapsed and then accreted material. The formation of the Milky Way's center is tied to the formation of the galaxy itself. In the early universe, gas clouds collapsed under gravity, stars formed, and in the densest regions, black holes formed. Over billions of years, these black holes merged and grew. Eventually, one became dominant. That's Sagittarius A asterisk. The process is gradual, chaotic, and difficult to observe directly. But simulations and observations of distant galaxies give us clues, and slowly we're piecing together the story of how our galaxy's heart came to be. The gas cloud spiraling inward. Around Sagittarius A, there's gas. Not a lot, compared to some active black holes, but enough to create an accretion disk. The gas spirals inward, pulled by gravity. As it spirals, it heats up. Friction and compression raise the temperature to millions of degrees, and the heated gas emits radiation. X-rays, radio waves, infrared light. The gas clouds spiraling inward are the black hole's food, but Sagittarius A is a picky eater. It doesn't consume much. Most of the gas is blown away by radiation pressure and magnetic fields. Only a small fraction actually crosses the event horizon. This makes Sagittarius A asterisk a quiet black hole. If it were feeding more aggressively, it would be much brighter. We'd see powerful jets, like those from other active galactic nuclei. But Sagittarius A asterisk is dormant. or at least sleepy. The gas is there. It's spiraling inward, but the feeding rate is low, and the black hole remains relatively dim. For now, the magnetic fields, twisting around the core. Magnetic fields permeate the region around Sagittarius A. They're generated by the motion of charged particles in the accretion disk, and they're incredibly strong. These fields twist and tangle as the disk rotates. They can channel material, funneling it toward the black hole, or they can launch it outward in jets. Though in Sagittarius A's case, no large-scale jets have been observed. The magnetic fields twisting around the core are crucial for understanding how black holes accrete material. They transport angular momentum, allowing gas to spiral inward, and they convert gravitational energy into radiation, making the accretion disk shine. Observing these fields is challenging. They're invisible to most telescopes, but radio observations can detect polarized light, which reveals the structure of magnetic fields, and new techniques are giving us better views of how these fields behave near the event horizon. The magnetic fields are not just background players, they're active participants in the physics of black holes, the streams of matter, drawn by gravity. Gravity doesn't just pull on gas, it pulls on everything. Stars, dust, even other black holes. Around Sagittarius A, streams of matter are constantly being drawn inward. Sometimes it's a diffuse gas, sometimes it's a denser cloud, and occasionally, it's something more substantial. In 2014, astronomers observed a gas cloud called D2 as it passed close to Sagittarius A. There was excitement. Would the black hole devour it? Would there be a bright flare? The cloud approached. It stretched under tidal forces, and then, nothing dramatic happened. The cloud passed by, slightly disrupted, but largely intact. The streams of matter drawn by gravity are continuous but sparse. Sagittarius A** is in a relatively empty region. The gas density is low, and the feeding rate is correspondingly low. This is why the black hole is so quiet. If it were in a denser environment, it would be much more active. The streams we do see reveal the complex dynamics near the black hole. Gas doesn't fall straight in. It swirls, it interacts with magnetic fields, and it heats up, emitting radiation that we can detect. Each stream is a small chapter in the ongoing story of the black hole's feeding habits. The X-ray flares from its surroundings. Sagittarius A* is usually quiet, but occasionally it flares. These flares are sudden increases in X-ray and infrared emission. They last for a few hours, then fade. The flares are thought to be caused by magnetic reconnection, events near the black hole. Magnetic field lines snap and reconnect, releasing energy, or perhaps by hot spots in the accretion disk, regions that briefly heat up and then cool down. The X-ray flares from its surroundings are unpredictable. They happen every few days or weeks, sometimes more often, sometimes less. Each flare is unique. Some are bright, others are dim, and studying them helps us understand the environment around the black hole. The flares tell us about the accretion process, about the magnetic fields, and about the dynamics of the gas near the event horizon. They're brief windows into the activity of Sagittarius A*, moments when the sleeping giant stirs, just a little, before settling back into quiet. The bursts of energy that reach across light years. When Sagittarius A* flares, the energy doesn't stay local, it spreads outward. X-rays and infrared light travel at the speed of light, reaching across the galactic center. Some of this radiation is absorbed by gas and dust, some is reflected, and some escapes, traveling across light years before being detected by our telescopes. The bursts of energy that reach across light years are echoes of activity near the black hole. They light up nearby nebulae, they heat gas clouds, and they create a faint glow that we can observe. These echoes tell us about the history of Sagittarius A*. When the light from a flare reaches a distant cloud and is reflected, we're seeing the flare as it was thousands of years ago. light travel time delays the signal, and by studying these echoes, we can reconstruct the black hole's past activity. The bursts are small compared to what active galactic nuclei produce, but they're still significant, and they remind us that even a quiet black hole is never truly silent. The radio waves that first revealed its presence. Radio waves were the key to discovering Sagittarius A. In the 1970s, when radio astronomy was still relatively new, astronomers turned their antennas toward the galactic center, and they heard something. A strong, persistent signal, radio emission from a compact source. The radio waves that first revealed its presence continue to be important. Radio observations can penetrate dust and gas. They're not blocked by the material that obscures visible light, and they provide crucial information about the black hole's environment. The radio emission comes from synchrotron radiation, electrons spiraling in magnetic fields, emitting radio waves. This tells us about the magnetic field strength, the electron density, and the dynamics of the accretion disk. Modern radio telescopes are far more powerful than those from the 1970s, and they've given us increasingly detailed views of Sagittarius A, leading, eventually, to the first image of its shadow. Radio waves opened the door, and they continue to reveal new secrets about the heart of our galaxy. The Very Large Array that heard its song. The Very Large Array, or VLA, is a radio telescope in New Mexico. It consists of 27 antennas arranged in a Y shape. Together, they act as a single, enormous telescope. The VLA was instrumental in studying Sagittarius A. It provided detailed radio maps of the galactic center. It measured the size and brightness of the radio source, and it helped confirm that Sagittarius A was something extraordinary. The Very Large Array that heard its song is still in operation. It's been upgraded over the years, becoming more sensitive and capable, and it continues to observe the galactic center, tracking changes in the radio emission. The VLA's observations complement those from other telescopes. Together, they build a complete picture of Sagittarius A asterisk, radio, infrared, X-ray. Each wavelength reveals different aspects, and each telescope adds a piece to the puzzle. The VLA's contribution to our understanding of black holes is immeasurable. It turned a faint signal into a cosmic discovery. The observations from Chandra X-ray Observatory. The Chandra X-ray Observatory is a space telescope launched in 1999. It observes the universe in X-rays, wavelengths that are blocked by Earth's atmosphere. Chandra has observed Sagittarius A asterisk for decades. It's detected the X-ray flares, it's mapped the hot gas around the black hole, and it's revealed the high-energy environment near the galactic center. The observations from Chandra X-ray Observatory have been crucial. X-rays tell us about the hottest, most energetic processes. Gas heated to millions of degrees, particles accelerated to near light speed, and the interactions between the black hole and its surroundings. Chandra's images show a complex, dynamic region. There are filaments of hot gas, clouds glowing in X-rays, and the occasional bright flare from Sagittarius A asterisk itself. Each observation adds to our understanding, and together they paint a picture of a black hole that's mostly quiet but occasionally active, a sleeping giant that stirs now and then, reminding us of its power. The glowing traces of heated gas. Around Sagittarius A, there's gas, and some of it is incredibly hot, heated to millions of degrees by shocks, by magnetic reconnection, or by compression as it spirals inward. This heated gas glows, in X-rays, primarily, but also in other wavelengths. The glowing traces of heated gas are visible in images from Chandra and other X-ray telescopes. They appear as bright filaments and clouds, structures that reveal the complex dynamics of the galactic center. Some of the gas is falling toward the black hole, some is being blown away by radiation pressure, and some is just sitting there, heated by past activity or by interactions with magnetic fields. The gas is a tracer. It shows us where energy is being deposited, where the magnetic fields are strongest, and where the black hole's influence is most direct. By studying the heated gas, we learn about the environment around Sagittarius A, about the processes that govern accretion, and about the black hole's impact on its surroundings. The infall of a gas cloud named G2. In 2011, astronomers discovered a gas cloud on a collision course with Sagittarius A asterisk. It was designated G2, and it was heading straight for the black hole. There was excitement. If G2 reached the black hole, it might trigger a bright flare or even a sustained increase in activity. Astronomers around the world prepared to observe. Telescopes were scheduled, predictions were made, and everyone waited. The infall of a gas cloud named G2 was expected to reach its closest approach in 2014, and it did. G2 stretched under tidal forces, it elongated, and it passed by the black hole. But nothing dramatic happened. No bright flare, no increase in activity, just a quiet passage. Why? Scientists aren't entirely sure. Perhaps G2 wasn't just a gas cloud. It might have had a star at its core, which held it together. Or perhaps the black hole is simply too inefficient at capturing material. Regardless, the event was instructive. It showed us that even close encounters don't always lead to dramatic results. The moment astronomers held their breath. In 2014, as G2 approached Sagittarius A, the astronomical community watched closely. Every major observatory pointed toward the galactic center, radio telescopes, infrared telescopes, X-ray satellites, all observing, all waiting. The moment astronomers held their breath was the closest approach, when G2 was predicted to pass within a few billion kilometers of the black hole. If something was going to happen, it would be now. But the black hole remained quiet. G2 passed by, disrupted, but not destroyed, and Sagittarius A barely reacted. There was disappointment, yes, but also fascination. The non-event was informative. It told us about the efficiency of accretion, about the structure of G2, and about the environment around the black hole. Sometimes, what doesn't happen is as important as what does. And the quiet passage of G2 was a reminder that the universe doesn't always deliver drama. Sometimes, it whispers instead. The cloud that survived the encounter. G2 survived. That was the surprise. Astronomers expected it to be torn apart, stretched into a long stream of gas, and possibly accreted by the black hole. But G2 held together. It emerged from the encounter, elongated, but intact. The cloud that survived the encounter revealed something important. G2 is likely not a pure gas cloud. It probably contains a star, a compact object at its core that provides gravitational cohesion. The gas is orbiting this core, and the core held everything together during the close approach. This discovery changed our understanding of objects near the black hole. Many of the clouds we observe might actually be stars with dusty or gaseous envelopes, and this has implications for how we interpret observations of the galactic center. G2's survival was a lesson. The universe is more complex than our models, and every observation, even when it doesn't match expectations, teaches us something new. G2 is still there, still orbiting, and still being studied. The strange calm of a sleeping black hole, Sagittarius A asterisk, is quiet, eerily quiet. Compared to other supermassive black holes, it's barely active. Some black holes at the centers of other galaxies shine brilliantly. They're called active galactic nuclei, or AGN. They emit powerful jets. They outshine their entire galaxies. But Sagittarius A asterisk does none of that. It's dim, sleepy, almost invisible. The strange calm of a sleeping black hole is puzzling. Why is Sagittarius A asterisk so quiet? The answer lies in its feeding rate. The black hole is starving. There's not much gas in its immediate vicinity, and what gas there is doesn't accrete efficiently. Most of it is blown away or remains in orbit. Without a steady supply of material, Sagittarius A asterisk can't sustain high levels of activity. It flickers, occasionally. It flares, but it never roars. The calm is temporary, though. In the past, Sagittarius A asterisk was more active, and in the future, it might wake up again. For now, we observe a sleeping giant, quiet, but never harmless. The low activity of Sagittarius A. Sagittarius A asterisk is one of the quietest supermassive black holes known. Its luminosity is incredibly low for its mass. If you calculate the Eddington limit, the maximum luminosity a black hole can sustain, while accreting, Sagittarius A asterisk is emitting only about 1/10 billionth of that. It's barely glowing. The low activity of Sagittarius A asterisk is both a blessing and a challenge. It's a blessing because it means our galactic center is relatively safe. We're not being bombarded by high-energy radiation. There are no powerful jets disrupting star formation, and the environment is stable, but it's a challenge for astronomers. Studying a dim black hole is difficult. The signals are weak. The variability is subtle, and it requires the most sensitive instruments. Still, the low activity allows us to study the black hole in detail. We can observe the orbits of stars without them being disrupted by outflows or radiation, and we can see the structure of the accretion disk without it being overwhelmed by luminosity. The signs that it once was fiercer. Sagittarius A asterisk is quiet now, but it wasn't always. Evidence suggests that in the past, perhaps a few million years ago, it was much more active. How do we know? From echoes. Light echoes. When the black hole was active, it emitted powerful radiation. That radiation traveled outward, illuminating gas clouds throughout the galactic center, and some of that radiation is still reaching distant clouds today. When the light hits a cloud, it's absorbed and re-emitted. We see the cloud glow, and by studying that glow, we can reconstruct the black hole's past activity. The signs that it once was fiercer are written in these echoes. They tell us that Sagittarius A asterisk was thousands or even millions of times brighter than it is now. It may have been an active galactic nucleus, feeding voraciously on gas and emitting powerful radiation. What caused the change? Likely a decrease in the gas supply. The black hole consumed the nearby material, and once the feast was over, it settled into dormancy. The echoes of ancient flares in galactic gas. Throughout the galactic center, there are clouds of gas. Some are glowing, emitting X-rays and other radiation, and the glow is an echo of activity from Sagittarius A asterisk that happened thousands of years ago. The light from that activity has been traveling through space. When it hits a gas cloud, the cloud absorbs the energy and re-emits it. We see the cloud light up, and by measuring the brightness and spectrum, we can determine when the original flare occurred. The echoes of ancient flares in galactic gas are time capsules. They preserve information about the black hole's past, and they allow us to study activity that happened long before we had telescopes. These echoes have revealed that Sagittarius A asterisk goes through cycles, periods of activity followed by periods of dormancy. The cycles might be linked to the availability of gas or to encounters with massive gas clouds. Each echo is a clue, and together they tell the story of a black hole that's anything but static. The X-ray reflections in nearby nebulae. Near Sagittarius A, there are several nebulae, clouds of gas and dust, some illuminated by nearby stars, others by the black hole itself. These nebulae reflect X-rays. When X-rays from a past flare hit the nebulae, they're scattered in our direction. We see a reflection. The X-ray reflections in nearby nebulae are like mirrors. They show us the black hole's past from different angles and at different times. Each nebulae is at a different distance, so the light travel time is different, and the reflection we see corresponds to a different moment in the black hole's history. By studying multiple nebulae, we can create a timeline. We can watch how the black hole's activity changed over thousands of years. It's a form of time travel, not literal, of course, but it allows us to observe the past, to see what Sagittarius A was doing when ancient civilizations were just beginning. The reflections are faint, but they're there, waiting to be studied. The Fermi bubbles, proof of a violent past. In 2010, astronomers discovered something astonishing: two enormous structures extending above and below the galactic plane. They're called the Fermi bubbles, named after the Fermi Gamma-ray space telescope that discovered them. Each bubble is about 25,000 light-years tall. Together, they dwarf the visible Milky Way. The Fermi bubbles are proof of a violent past. They're filled with high-energy gamma rays and X-rays, and their shape suggests they were created by a massive outburst from the galactic center, possibly from Sagittarius A asterisk itself. The leading theory is that a few million years ago, the black hole went through a period of intense activity. It fed on a large amount of gas, and the energy released created powerful jets or winds. Those jets carved out the bubbles, pushing gas and energetic particles far above and below the galaxy. The bubbles are still there, still glowing, a relic of ancient violence, and a reminder that Sagittarius asterisk is capable of much more than we currently observe. The giant structures above and below the galaxy. The Fermi bubbles are enormous. They extend roughly 25,000 light-years above the galactic plane and 25,000 below. That's about half the diameter of the visible Milky Way disk, and they're filled with energetic particles, cosmic rays, gamma rays, X-rays. The giant structures above and below the galaxy are perpendicular to the galactic disk. They're symmetrical, and they have sharp edges, suggesting they were created relatively recently. In cosmic terms, the origin of the bubbles is still debated. Most scientists think they're related to past activity from Sagittarius A asterisk, but some propose they're related to intense star formation in the galactic center. Either way, they're evidence of enormous energy release. The bubbles are difficult to see in visible light, but in gamma rays and X-rays, they're prominent, and studying them gives us insights into the history of the galactic center, into the processes that shape galaxies, and into the power that supermassive black holes can wield. The energy left from long-ago outbursts. The Fermi bubbles contain a staggering amount of energy. Estimates suggest they represent about 10 circumflex 56 ergs. That's equivalent to about 100,000 supernovae. All that energy was released in a relatively short time, perhaps a few million years, and it's still present, filling the bubbles with hot gas and energetic particles. The energy left from long-ago outbursts doesn't just sit there. It interacts with the surrounding medium. It heats gas, it accelerates particles, and it influences the structure of the galaxy. The bubbles are expanding, slowly, and as they expand, they're doing work on the interstellar medium, pushing it, shaping it, creating structures that we can observe. This energy is a form of feedback. The black hole feeds, it releases energy, and that energy affects the galaxy. It can suppress star formation by heating gas, or it can trigger star formation by compressing gas. The interplay is complex, but it's crucial for understanding how galaxies evolve. The connection between black holes and galaxy growth. Supermassive black holes don't just sit at the centers of galaxies. They play an active role in galactic evolution. As they feed, they release energy, and that energy influences star formation, gas distribution, and the overall structure of the galaxy. The connection between black holes and galaxy growth is one of the major discoveries of modern astrophysics. Observations show that the mass of a galaxy's central black hole is correlated with the mass of the galaxy's bulge. This suggests they co-evolve, they grow together. The mechanism is feedback. When a black hole feeds, it emits radiation, and sometimes jets. That energy heats the surrounding gas, preventing it from cooling and collapsing to form stars. This regulates star formation. It prevents galaxies from forming stars too quickly. Sagittarius A asterisk is part of this story. Its past activity likely influenced the Milky Way's evolution, and its current dormancy might be allowing star formation to proceed in the galactic center. The connection is subtle, but it's fundamental. Black holes aren't passive. They're active shapers of the universe. The central engine that shapes the Milky Way. At the heart of the Milky Way, Sagittarius A asterisk acts as a central engine, not in the sense that it powers everything, but in the sense that it organizes. It defines the center. It influences the orbits of stars, and its past activity has shaped the distribution of gas. The central engine that shapes the Milky Way is mostly dormant now, but it's still there, still exerting its influence. The black hole's gravity anchors the nuclear star cluster, and the energy it releases, even at low levels, affects the surrounding environment. In other galaxies, the central engine is more obvious. Active galactic nuclei shine brilliantly. They emit jets that extend for thousands or millions of light years, and they dominate their galaxies. Sagittarius A asterisk doesn't do that, but the potential is there. If the gas supply increases, if a large cloud falls in, the engine could roar to life, and the Milky Way would look very different. For now, we have a quiet center, but it's not asleep, just resting. The feeding habits of a quiet giant, Sagittarius A asterisk, is a picky eater. It's surrounded by gas, but it doesn't consume much of it. Simulations suggest that only about 1% of the available gas actually crosses the event horizon. The rest is blown away or remains in orbit. The feeding habits of a quiet giant are inefficient. The gas spirals inward, forming an accretion disk. But the disk is hot and diffuse. Radiation pressure pushes gas outward. Magnetic fields channel it away, and most of the material never reaches the black hole. This inefficiency is why Sagittarius A asterisk is so dim. If it were more efficient, it would be much brighter. It would be an active galactic nucleus, but instead, it's starving, barely glowing. The feeding habits also vary. Sometimes Sagittarius A asterisk accretes a bit more. There's a flare, a brief increase in luminosity, and then it settles back into quiet. The giant is always hungry, but it rarely gets a satisfying meal. The occasional bursts of energy we still detect. Even though Sagittarius A asterisk is quiet, it's not completely dormant. Every few days or weeks, there's a flare, a sudden increase in X-ray or infrared emission. These flares are brief, lasting a few hours, and then they fade. The occasional bursts of energy we still detect are windows into the black hole's activity. They're thought to be caused by magnetic reconnection or by hot spots in the accretion disk, regions that briefly heat up and emit more radiation. Each flare is unique. Some are bright, others are dim, and studying them helps us understand the dynamics near the event horizon. The flares are unpredictable. They don't follow a pattern, and that makes them challenging to study. But they're also valuable. They provide snapshots of the environment around the black hole, and they reveal processes that are otherwise hidden. The bursts remind us that even a sleeping giant is never truly still. It stirs, it flickers, and it shows us its power, if only briefly. The black hole's accretion disk. Around Sagittarius A, there's an accretion disk, a swirling disk of gas and dust, spiraling inward toward the event horizon. The disk is fed by material from stellar winds, from disrupted stars, and from gas clouds passing by. As the gas spirals inward, it heats up. Friction and compression raise the temperature. In the inner regions, near the event horizon, the gas reaches millions of degrees, hot enough to emit X-rays. The black hole's accretion disk is not a solid structure. It's turbulent, chaotic. Magnetic fields twist through it, Convection currents churn it, and it's constantly changing. The disk is also relatively dim in Sagittarius A's case because the accretion rate is low, but it's still there, still glowing, and still providing material for the occasional flare. The accretion disk is the interface between the black hole and the outside universe. It's where material makes its final journey, where energy is extracted from gravity, and where we can observe the black hole's influence. The material heated to millions of degrees. In the inner regions of the accretion disk, temperatures soar. The gas is heated by friction, by compression, and by magnetic reconnection. Temperatures reach tens of millions of Kelvin. At these temperatures, the gas is completely ionized. It's a plasma, electrons and ions moving at incredible speeds. The material heated to millions of degrees emits X-rays, high-energy photons that escape the accretion disk and travel across the galaxy. When we observe Sagittarius A asterisk in X-rays, we're seeing this hot material. It's a direct probe of the environment near the event horizon. The heating process is efficient at converting gravitational energy into radiation. As gas falls inward, it releases energy. About 10% of its rest mass energy can be extracted through accretion. That's more efficient than nuclear fusion. The hot material doesn't last long. It either falls into the black hole or is blown away. But while it's there, it glows, bright and fierce, a testament to the power of gravity. The plasma spiraling near light speed. In the innermost regions of the accretion disk, the gas is moving fast, very fast. Orbital velocities approach a significant fraction of the speed of light. At the innermost stable circular orbit, about 3 times the event horizon radius, material is moving at about 40% light speed. The plasma spiraling near light speed experiences extreme conditions, time dilation, gravitational redshift, frame dragging from the black hole's rotation. These effects are predicted by general relativity, and they've been observed, at least indirectly. The spectrum of the accretion disk shows broadening. The light from the disk is smeared out by Doppler effects. Material moving toward us is blue shifted. Material moving away is red shifted. And the result is a characteristic broadened emission line. This broadening tells us about the velocities near the black hole, and it confirms that general relativity accurately describes the strong field regime. The plasma near the event horizon is a laboratory for testing physics at its limits, and Sagittarius A asterisk provides a unique opportunity to study it. The shadow of a black hole becomes visible. For decades, black holes were theoretical. We could infer their existence. We could measure their mass, but we couldn't see them. They were invisible by definition. But in 2022, that changed. The Event Horizon Telescope collaboration released an image of Sagittarius A, not an image of the black hole itself, but an image of its shadow. The shadow of a black hole becomes visible through gravitational lensing. Light from the accretion disk is bent around the black hole, and in the center, where no light can escape, there's darkness. A shadow. That shadow is what the Event Horizon Telescope captured. It's a blurry ring of light, orange and red, with a dark center. It's not much to look at, visually, but scientifically, it's a revolution. It's proof that Sagittarius A is real, that it's a black hole, and that general relativity accurately predicts what black holes look like. The shadow is about 52 micro-arcseconds across. That's incredibly small, about the size of a donut on the moon as seen from Earth. The Event Horizon Telescope Project. The Event Horizon Telescope, or EHT, is not a single telescope. It's a network, a global array of radio telescopes working together. They're synchronized to observe the same target at the same time, and their combined data creates an Earth-sized virtual telescope. The Event Horizon Telescope project began in earnest in the 2010s. The goal was ambitious. To image the shadow of a black hole, two targets were chosen: Me-87, the supermassive black hole in the galaxy, M87, and Sagittarius A. In 2017, the EHT observed both targets. Telescopes in Hawaii, Arizona, Mexico, Chile, Spain, and Antarctica all pointed at the galactic center. For several days, they collected data, petabytes of data, too much to transmit over the internet. The data was stored on hard drives and shipped to central locations. And then the real work began, correlating the data, reconstructing the image, and confirming that what they saw was real. The project was a triumph of international collaboration, and it delivered one of the most important images in the history of astronomy: the network of observatories around Earth. The EHT consists of multiple radio observatories spread across the globe. Each one is a piece of the puzzle. The Atacama Large Millimeter Array in Chile, the Sub-Millimeter Telescope in Arizona, the IRAM 30-meter telescope in Spain, the South Pole Telescope in Antarctica, and several others. The network of observatories around Earth acts as a single planet-sized telescope. The technique is called Very Long Baseline Interferometry, or VLBI. It uses the rotation of the Earth to change the relative positions of the telescopes, and from those changing positions, it reconstructs an image. The resolution of a telescope depends on its size. The larger the telescope, the finer the details it can see. By using the entire Earth as a telescope, the EHT achieves a resolution of about 20 micro-arcseconds. That's sharp enough to resolve the shadow of Sagittarius A*. The network is still growing. New telescopes are being added, and the images will get sharper. But even with the current network, the results are stunning. The first image of Sagittarius A in 2022. On May 12, 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A. It was a historic moment. The image showed a blurry ring of orange light, brighter in some regions, dimmer in others, and in the center, darkness, the shadow of the black hole. The first image of Sagittarius A in 2022 was years in the making. The observations were done in 2017, but processing the data took time. Sagittarius A* is variable. It changes on timescales of minutes, and that made it challenging to create a stable image. The team had to develop new algorithms, new techniques for averaging the data, and new ways to confirm that the image was real. The result was worth the wait. The image confirmed that Sagittarius A* is a black hole. It matched the predictions of general relativity, and it showed the world what the heart of our galaxy looks like: a shadow, a void, surrounded by light, the blurry ring of light that changed astronomy. The image of Sagittarius A* isn't sharp. It's blurry, pixelated, almost abstract, but it's revolutionary. The blurry ring of light that changed astronomy is proof that black holes exist, proof that we can image them, and proof that our theories are correct. The ring is the photon sphere, the region where light orbits the black hole. Some of that light escapes and reaches us, and it creates the bright ring we see. The dark center is the shadow, the region where no light can escape. It's larger than the event horizon because of gravitational lensing. The image has been compared to other famous astronomical images: the first image of the surface of Mars, the first image of the Earth from space, the first image of a planet orbiting another star. Each one changed how we see the universe, and Sagittarius A's image is no different. It's a milestone, a moment when the invisible became visible, the confirmation of Einstein's predictions. Einstein's general relativity has been tested many times, and it's passed every test. But the image of Sagittarius A* is one of the strongest confirmations yet. General relativity predicts exactly what a black hole should look like: the size of the shadow, the shape of the ring, the way light bends, and the EHT image matches those predictions perfectly. The confirmation of Einstein's predictions is profound. It shows that general relativity works even in the most extreme environments. Near the event horizon of a black hole, where gravity is strongest, there were alternative theories, modified gravity, quantum corrections. But the image rules most of them out. What we see is exactly what Einstein's equations predict. The shadow is the right size, the ring is the right shape, and the brightness distribution matches simulations. Einstein, who died in 1955, never imagined we'd be able to photograph a black hole, but his equations anticipated it, and now we've confirmed he was right. The shape of space-time made visible. The image of Sagittarius A asterisk is more than a picture. It's a visualization of space-time. The bright ring is light that's been bent by gravity, curved around the black hole. The shape of space-time made visible is what we're seeing. Space-time isn't flat near the black hole. It's warped, twisted, and that warping affects the path of light. Light that would normally travel in a straight line is bent. It curves around the black hole, and from our perspective, it creates a ring. The ring is larger than the event horizon. It's about 2.6 times the radius. That's because light can orbit the black hole, and some of that orbiting light escapes. The image is a direct view of curved space-time. Its geometry made visible, and it's one of the most profound images in science. We're not just seeing a black hole, we're seeing the fabric of the universe itself, bent, twisted, and revealed through light. The comparison with Men-87's black hole, Sagittarius A asterisk, isn't the only black hole we've imaged. In 2019, the Event Horizon Telescope released an image of M87, the supermassive black hole at the center of the galaxy M87. M87 is much larger than Sagittarius A. It contains about 6.5 billion solar masses, and its event horizon is correspondingly larger. The comparison with M87's black hole is instructive. Both images show the same basic structure: a bright ring, a dark center, but there are differences. M87 has a prominent jet. Sagittarius A asterisk does not. M87 asterisk is relatively stable. Sagittarius A asterisk is variable. Despite the differences, the images confirm the same physics. Black holes, regardless of size, behave as Einstein predicted. They create shadows, they bend light, and they reveal the structure of space-time. The two images together provide a powerful confirmation. Black holes exist, they're real, and we can see them, not directly, but through their shadows. And that's almost as good. The smallest object ever imaged, at galactic scale. The shadow of Sagittarius A asterisk is tiny, about 52 microarc seconds across. That's an incredibly small angle. To put it in perspective, it's like viewing a grape on the moon from Earth. The smallest object ever imaged at galactic scale is a testament to human ingenuity. We've built telescopes that can resolve features across 26,000 light-years. We've developed algorithms that can process petabytes of data, and we've confirmed that the heart of our galaxy is a black hole. The image is at the resolution limit of what's possible with current technology. To see more detail, we'd need an even larger telescope, perhaps one in space, or one with more telescopes added to the network. But even at this resolution, the image is revolutionary. It shows us the shadow, it confirms general relativity, and it opens a new era of black hole astronomy. The smallest object we've imaged is also one of the most important. It's the heart of our galaxy, and now we can see it. The challenges of photographing the invisible. Photographing a black hole is paradoxical. Black holes don't emit light, they absorb it. So how do you photograph something invisible? The answer is, you don't. You photograph what's around it: the glowing gas, the bent light, the shadow cast against the brightness. The challenges of photographing the invisible are immense. First, the target is tiny. Sagittarius A asterisk is only 52 microarc seconds across as seen from Earth. That requires unprecedented resolution. Second, it's variable. The black hole's environment changes on timescales of minutes, faster than we can take a clear image. Third, it's obscured. Dust and gas scatter the light, blurring the image. And fourth, it requires global coordination, multiple telescopes observing simultaneously, data synchronized to nanoseconds. Each challenge was overcome through innovation, adaptive algorithms that account for variability, techniques to correct for scattering, and a network of observatories working as one. The result is an image of the invisible, a photograph of a shadow, and a triumph of human persistence. The data collected across continents. During the 2017 observations, the Event Horizon Telescope collected an enormous amount of data, about 5 petabytes. That's 5 million gigabytes, enough to fill thousands of hard drives. The data collected across continents couldn't be transmitted electronically. The internet isn't fast enough. Instead, the data was recorded on hard drives at each observatory. Those drives were then physically shipped to central processing facilities, one in Germany, one in the United States. The data from Antarctica took months to arrive. It had to wait until the end of the Antarctic winter, when flights could resume. Once all the data arrived, the correlation began. Computers compared the signals from different telescopes. They looked for patterns, coincidences, and from those patterns, they reconstructed the image. The process was computationally intensive. It required supercomputers, and it took years. But the result was worth it. An image that revealed the heart of the Milky Way. The supercomputers that reconstructed the image. Processing the data from the Event Horizon Telescope required supercomputers, powerful machines capable of handling petabytes of information. The data had to be correlated. Signals from different telescopes had to be aligned and compared. And then algorithms had to reconstruct an image from the patterns. The supercomputers that reconstructed the image ran for months. They performed trillions of calculations. They tested different imaging techniques, and they produced multiple versions of the image to ensure consistency. The algorithms were sophisticated. They had to account for the variability of Sagittarius A asterisk. They had to average over time without blurring the essential features, and they had to remove artifacts introduced by the atmosphere and the observing process. The result was several independent images, created using different algorithms, different assumptions, and when those images were compared, they matched. The ring was there, the shadow was there, and the structure was consistent. That consistency gave scientists confidence. The image was real. The proof that Sagittarius A is real. For decades, Sagittarius A asterisk was inferred, calculated, deduced from the motions of stars. But there was always room for doubt. Could it be something else? A cluster of dark objects? A concentration of dark matter? Some exotic alternative? The proof that Sagittarius A asterisk is real came in 2022. The image of its shadow, the dark center, surrounded by a bright ring. It matched the predictions for a black hole exactly. No alternative explanation fit. The shadow is the right size, about 52 microarc seconds. That corresponds to a mass of about 4 million suns. Exactly what was calculated from stellar orbits. The shape is circular, as expected for a black hole, and the brightness varies around the ring, consistent with the rotation of the accretion disk. The proof is undeniable. Sagittarius A asterisk is a supermassive black hole. It's at the center of our galaxy, and now we've seen its shadow. The decades of research, the observations, the calculations, they all led to this moment, confirmation. The cosmic shadow that defines the Milky Way. The shadow of Sagittarius A asterisk is more than just a dark spot. It's a defining feature of our galaxy. The cosmic shadow that defines the Milky Way is the signature of the black hole's presence. It's the absence of light where light cannot exist. The shadow is created by the event horizon, or more precisely, by the region just around it. Light that gets too close is captured, it spirals inward, and it's lost forever. The result is a dark circle surrounded by light that was bent but not captured. That shadow is stable. It doesn't change with time. Even though the accretion disk is variable, the shadow remains. It's determined by the mass and spin of the black hole, and those properties don't change on human timescales. The shadow is a marker, a sign that says here lies a black hole, and it's now one of the most famous shadows in the universe. The heart of our galaxy, made visible through its absence. The motions of gas in its vicinity. Around Sagittarius A asterisk, gas is in constant motion. It swirls, it spirals, it heats up and cools down. The motions are chaotic on small scales, but organized on large scales. The motions of gas in its vicinity are governed by gravity and magnetic fields. Gravity pulls the gas inward, magnetic fields channel it, and radiation pressure pushes it outward. The result is a complex dance. The gas forms an accretion disk, but it's not a simple, smooth disk. It's turbulent. There are eddies, hot spots, regions of higher and lower density, and the gas is moving fast. Near the event horizon, orbital velocities approach the speed of light. Farther out, they're slower, but still significant. Studying the gas motions helps us understand accretion, how material falls into a black hole, how energy is extracted, and how the environment responds to the black hole's gravity. It's a window into one of the most fundamental processes in astrophysics. The orbits that dance around the center. The S-stars dance around Sagittarius A asterisk. Their orbits are ellipses, some tight, some elongated. Each star follows its own path, dictated by gravity. The orbits that dance around the center are like clockwork, predictable, measurable, and incredibly fast. C2, the best-studied star, completes its orbit in 16 years. That's fast for a star. Earth takes 1 year to orbit the Sun. C2 takes 16 to orbit a black hole millions of times more massive. Other stars have different periods, some longer, some shorter. C62, one of the fastest, completes an orbit in less than 10 years. The orbits are not perfectly fixed. They precess. The ellipse rotates over time. This precession is a relativistic effect. Newton's gravity would predict no precession, but Einstein's gravity does, and the observations match Einstein's predictions. The dancing orbits are proof of the black hole's mass, proof of general relativity, and proof that we can study extreme gravity using stars as test particles. The extreme time dilation near its edge. Time near a black hole runs slower than time far away. This is gravitational time dilation, a prediction of general relativity, and near Sagittarius A asterisk. The effect is significant. At the innermost stable orbit, about 3 times the event horizon radius, time runs at about 50% the rate it does far away. A clock there would tick half as fast as a clock on Earth. The extreme time dilation near its edge affects everything. Light is redshifted, processes appear slower, and the perception of time changes. For someone falling toward the black hole, time would pass normally, but for an outside observer, the person would appear to slow down. Approaching the event horizon, they'd seem to freeze, their light would fade, and they'd appear to hover at the edge forever. The time dilation has been measured, not directly, but through the light from hot gas near the black hole. The gas emits radiation, and that radiation is redshifted by the intense gravity. The amount of redshift tells us about the time dilation, and it confirms Einstein's predictions. The second-by-second stretch of reality. Near the event horizon, every second is stretched. Time dilates. Space curves. and reality becomes something different from what we experience in everyday life. The second-by-second stretch of reality is what makes black holes so strange. A second, near the event horizon, might correspond to minutes, hours, or even days far away. It depends on how close you are. At the event horizon itself, time effectively stops. From an outside perspective, a clock at the horizon would freeze, its ticking would slow to zero, and it would remain frozen forever. But from the clock's perspective, nothing unusual happens. Time passes normally. It ticks, it measures seconds, and it crosses the horizon without incident. This duality is one of the paradoxes of black holes. Different observers see different things, and both perspectives are valid. The stretch of reality near a black hole is a reminder that time is not absolute, it's relative, and in extreme gravity, it becomes unrecognizable. The theories tested by its existence. Sagittarius A asterisk is a laboratory, a place where we can test our theories of gravity, of accretion, of black hole physics, and every observation provides a test. The theories tested by its existence include general relativity. Einstein's theory has been confirmed again and again. The orbits of the S-stars show precession. The light from the accretion disk shows gravitational redshift, and the shadow matches the predicted size and shape. But there are other theories too, modified gravity theories, that try to explain dark matter or dark energy. Alternative theories of black holes, theories involving quantum effects. Each observation of Sagittarius A asterisk constrains these theories. Some are ruled out, others remain viable, and slowly we narrow down the possibilities. Sagittarius A asterisk is unique. It's close enough to study in detail, and massive enough to show strong gravitational effects. It's the perfect laboratory for testing our understanding of the universe. The evidence supporting general relativity. Every observation of Sagittarius A asterisk supports general relativity. The orbits of the S-stars match Einstein's predictions. The precession, the time dilation, the gravitational redshift, all exactly as predicted. The shadow of the black hole is the right size, about 52 microarc seconds. That corresponds to the Schwarzschild radius for a black hole of 4 million solar masses, and the shape is circular. As expected for a non-rotating or slowly rotating black hole, the evidence supporting general relativity is overwhelming. There are no discrepancies, no anomalies that can't be explained. General relativity has passed every test, and Sagittarius A asterisk is one of the strongest tests. It's a regime of extreme gravity, where space-time is highly curved, and where alternative theories would show deviations. But none do. Einstein was right, even in the most extreme environments we can observe. His theory holds, and Sagittarius A asterisk proves it. The question of quantum gravity still unanswered. General relativity describes gravity at large scales, but at very small scales, near the singularity of a black hole, it breaks down. It predicts infinite densities, infinite curvatures, and that's unphysical. The question of quantum gravity still unanswered is one of the biggest mysteries in physics. How do we combine general relativity with quantum mechanics? How do we describe gravity at the smallest scales? We don't know. There are candidate theories, string theory, loop quantum gravity, others, but none are proven, and none make testable predictions that we can currently observe. Sagittarius A asterisk doesn't solve this problem. The event horizon is still too large. The quantum effects are too small to detect, but it's a step. It's a regime where gravity is strong, and future observations, with better instruments, might provide clues. The question remains open, but Sagittarius A asterisk is part of the search, a place where we can push our theories to their limits and see where they break. The singularity hidden beyond the horizon. At the very center of Sagittarius A asterisk, according to general relativity, there's a singularity, a point of infinite density, where all the mass is compressed into zero volume. The singularity, hidden beyond the horizon, is unreachable. We can't observe it. We can't send probes to it. It's behind the event horizon, forever hidden, and that's probably for the best, because the singularity is where physics breaks. General relativity predicts it, but also admits it can't describe it. Quantum effects, which are ignored in general relativity, must become important, and we need a theory of quantum gravity to understand what's really there. Perhaps the singularity isn't a point. Perhaps it's a region of extremely curved space-time, or perhaps it's something else entirely. A quantum foam, a bounce, a connection to another universe. We don't know, and we may never know. The singularity is hidden, protected by the event horizon, and the universe doesn't let us see what's inside. The point where all physics breaks. The singularity is where our equations fail, where general relativity produces infinities, and where we need new physics. The point where all physics breaks is a humbling reminder. Our theories are good. They describe the universe with incredible accuracy, but they're not complete. There are regimes we don't understand, conditions we can't describe, and the singularity is one of them. At the singularity, density is infinite, curvature is infinite, and our usual concepts of space and time don't apply. It's a boundary of knowledge, a place where we have to admit we don't know. But science doesn't stop at the unknown. It pushes forward. It searches for new theories, new experiments, new observations, and slowly we expand the boundary. The singularity is a challenge, an invitation, a reminder that there's always more to learn, and that the universe still holds secrets we haven't uncovered. The mystery of what lies inside. What's inside a black hole? Beyond the event horizon, past the point of no return. What's there? The mystery of what lies inside is profound. We can't observe it, we can't measure it, and we can only speculate. According to general relativity, once you cross the event horizon, you're on a one-way trip to the singularity. Space and time swap roles. All paths lead inward, and you reach the singularity in a finite amount of proper time. But what's the singularity really like? Is it a point, a region? Does time end there? Does space, or do quantum effects save you? Perhaps there's a bounce. Perhaps you emerge in another universe. These are speculations, wild ideas, but they're based on serious physics. The mystery is unsolved, and it might remain unsolved. The event horizon is a one-way barrier. Information can go in, but it can't come out. And without information, we can't know. The inside of a black hole remains one of the greatest mysteries in science. The speculations about wormholes and portals. Some physicists have speculated that black holes might be wormholes, tunnels through space-time connecting distant regions of the universe, or even different universes. The speculations about wormholes and portals are fascinating, but they're just that. Speculations. There's no evidence, no observations that suggest black holes connect to anywhere else. Wormholes are solutions to Einstein's equations. They're mathematically possible, but they're also highly unstable. They collapse almost instantly unless held open by exotic matter, matter with negative energy, and we don't know if such matter exists. Still, the idea persists. Could Sagittarius A asterisk be a portal? Could you travel through it and emerge somewhere else? Almost certainly not. Even if wormholes exist, crossing one would be fatal. The tidal forces would tear you apart, and the journey would be one way. The speculations are fun. They inspire science fiction. But for now, they remain firmly in the realm of imagination. Black holes are dead ends, not portals. The boundary between science and imagination. Black holes push us to the edge. The boundary between science and imagination. Between what we know and what we wonder. We know black holes exist. We've measured their mass. We've imaged their shadows. but we don't know what's inside. We don't know what happens at the singularity, and we don't know if there are exotic possibilities, like wormholes. The boundary between science and imagination is where progress happens, where we ask, what if, and then try to find out, where we speculate, then test, where imagination guides science, and science constrains imagination. Sagittarius A asterisk sits on that boundary. It's real, measurable, observable, but it's also mysterious, strange, and full of unknowns. And that's what makes it so compelling. It's a reminder that the universe is larger than our theories, more complex than our models, and always ready to surprise us. The black hole as a cosmic historian. Black holes, remember. In a sense, they record information about everything that's ever fallen into them. The mass, the angular momentum, the charge. These properties are preserved, and they tell a story. The black hole as a cosmic historian is a poetic idea. Sagittarius A asterisk has been at the center of the Milky Way for billions of years. It's accreted gas, swallowed stars, and grown from a smaller seed into the 4 million solar mass giant it is today. All that history is encoded in its properties. The mass tells us how much it's consumed. The spin tells us about the direction and rate of accretion, and the environment around it tells us about recent activity. By studying Sagittarius A asterisk, we're reading the galaxy's history. We're learning about the early universe, about galaxy formation, and about the processes that shaped the Milky Way. The black hole is a record keeper, silent but informative, and every observation adds a page to the story. The record keeper of galactic evolution. Sagittarius A asterisk has witnessed the entire history of the Milky Way. It was there when the galaxy formed, when the first stars ignited, when the spiral arms took shape, and it's still there now. The record keeper of galactic evolution holds clues about our past. Its mass tells us about the merger history of the galaxy. Its spin tells us about the accretion history, and its environment tells us about the current state. Supermassive black holes are thought to grow along with their host galaxies. They co-evolve as the galaxy merges with others. The black holes merge too. Each merger adds mass and changes the spin. Sagittarius A's properties are the result of billions of years of evolution, and by studying it, we learn about the Milky Way's past, about the collisions, the mergers, the periods of intense star formation. The black hole remembers, and we're learning to read its memory. The clues about our galaxy's past. Every observation of Sagittarius A asterisk provides clues about where the Milky Way came from, how it grew, and what it will become. The clues about our galaxy's past are written in the black hole's properties. The mass suggests the Milky Way has undergone several mergers. Each merger brought new material, new gas, and new mass for the black hole. The spin, which is still being measured, will tell us about the direction of accretion, whether it's been consistent or chaotic. The Fermi bubbles tell us about past activity. A few million years ago, Sagittarius A asterisk was feeding. It was active, and it released enormous energy. That activity shaped the galaxy. It heated gas, it drove winds, and it left structures we can still observe. The clues are scattered in the stars, in the gas, in the black hole itself, and slowly we're putting them together, reconstructing the history of our galaxy, from its birth to the present day. The stars born in its vicinity. Near Sagittarius A asterisk, there are young stars, massive, hot, blue stars. They shouldn't be there. Star formation requires cold, dense gas, but near a black hole, the environment is anything but conducive. The gravity is intense, the tidal forces are strong, and the radiation from past activity should have heated the gas. Yet the stars are there, young and bright. How did they form? The stars born in its vicinity are a puzzle. One theory is that they formed farther out and migrated inward. Perhaps they were part of a cluster that was disrupted. Another theory is that they formed in a massive disk of gas that somehow survived near the black hole, a disk thick and dense enough to shield its interior from radiation. The truth is, we're not sure, but the stars are real, and they're teaching us that star formation is more robust than we thought. Even in the most extreme environments, stars find a way. The extreme conditions near the core. The galactic center is not a friendly place. The conditions there are extreme: high radiation, intense gravity, strong magnetic fields, and frequent stellar interactions. The extreme conditions near the core make it a unique environment. Stars orbit faster, gas is hotter, and magnetic fields are stronger. Any planet there would be bathed in radiation: X-rays from the black hole, cosmic rays from supernovae. It would be uninhabitable, but it's fascinating. The extreme conditions are a laboratory, a place where we can study physics at its limits, where gravity is strong, where energy densities are high, and where our theories are pushed to their breaking points. The galactic center is a harsh environment, but it's also a place of incredible beauty, of powerful forces, and of profound scientific interest. It's where the Milky Way's heart beats, and it's unlike anywhere else in the galaxy. The young stars that shouldn't exist there. The young stars near Sagittarius A asterisk are an anomaly. They're only a few million years old, in a region where star formation should be suppressed. The young stars that shouldn't exist there challenge our understanding. How did they form? Why are they there? And what does their presence tell us about the history of the galactic center? One possibility is that they formed during a brief period when conditions were right. Perhaps a large gas cloud fell toward the center, dense enough to collapse despite the harsh environment, and from that cloud, a burst of star formation occurred. Another possibility is that the stars formed elsewhere and were captured, or that they're the remnants of a disrupted star cluster. Each theory has challenges, and observations are ongoing, but the young stars are real, and they're a reminder that the universe is full of surprises. Even in places where we think we understand the rules, nature finds exceptions. The puzzle of star formation near black holes. Star formation near supermassive black holes is a puzzle. The environment should be hostile. Radiation should heat the gas. Tidal forces should disrupt clouds. And yet, stars form. The puzzle of star formation near black holes is being studied in multiple galaxies, not just the Milky Way. In many galactic centers, there are young stars, massive star clusters, and ongoing star formation. How? One theory involves shielding. If the gas is dense enough, the outer layers can absorb radiation, protecting the interior and allowing it to collapse. Another theory involves magnetic fields. Strong fields can channel gas, concentrating it into dense regions where star formation can occur. And a third theory involves feedback. Perhaps the black hole's activity, paradoxically, triggers star formation by compressing gas or by creating shocks. The puzzle isn't solved, but we're making progress, and every observation brings us closer to understanding how stars and black holes coexist. The streams of matter feeding its growth. Sagittarius A asterisk is growing, slowly. Every bit of gas that crosses the event horizon adds to its mass. The streams of matter feeding its growth are thin. The accretion rate is low, only about 10 circumflex 7 solar masses per year. That's a tiny fraction of a sun per year. At this rate, it would take trillions of years to double in mass. But the growth is real, and it's continuous. Gas spirals inward. Stars occasionally get too close and are tidally disrupted, and the black hole consumes the debris. Over the lifetime of the Milky Way, Sagittarius A asterisk has grown from a smaller seed into the giant it is today. How much larger will it become? That depends on the gas supply. If the Milky Way merges with Andromeda in a few billion years, the black holes will merge too, and Sagittarius A asterisk will become even more massive. The streams are small, but over cosmic time, they add up. The interplay between gravity and energy. Near Sagittarius A, two forces dominate. Gravity pulls inward, energy pushes outward. The interplay between gravity and energy shapes the environment. Gravity tries to pull everything toward the black hole, gas, stars, light, but energy resists. Radiation from the accretion disk heats gas, preventing it from falling in. Magnetic fields channel material, launching it outward in winds, and the rotation of the disk creates centrifugal forces, keeping material in orbit. The balance is delicate. If gravity dominates, accretion is efficient. The black hole feeds rapidly, and it shines brightly. If energy dominates, accretion is suppressed. The black hole starves, and it dims. In Sagittarius A's case, energy dominates. Most of the gas is blown away. Only a small fraction accretes, and the black hole remains quiet. The interplay is dynamic, constantly shifting, and it's what makes black hole accretion such a complex process. The magnetic fields that weave around it. Magnetic fields are everywhere around Sagittarius A. They thread through the accretion disk. They twist and tangle, and they play a crucial role in the physics. The magnetic fields that weave around it are generated by the motion of charged particles. As the plasma in the accretion disk rotates, it drags magnetic field lines with it. Those lines become twisted, and they store energy. When the twisting becomes too extreme, the fields can snap, reconnecting in a different configuration and releasing energy in the process. This magnetic reconnection might be the source of the flares we observe. The fields also transport angular momentum, allowing gas to spiral inward. Without magnetic fields, accretion would be much less efficient, and the black hole would feed less. The magnetic environment around Sagittarius A is complex, strong, and dynamic, and it's essential to understanding how the black hole interacts with its surroundings. The jets that never formed, a mystery of silence. Many supermassive black holes produce jets, powerful beams of material and energy, shot out from near the poles. These jets can extend for thousands or millions of light years, but Sagittarius A* has no jets, or at least no large-scale jets. The jets that never formed are a mystery of silence. Why doesn't Sagittarius A* produce jets? It has everything needed: a rotating black hole, an accretion disk, magnetic fields, and yet there are no jets. One possibility is that the black hole's spin is too low. Jets are thought to be powered by the rotation of the black hole. If Sagittarius A* is spinning slowly, it might not generate enough energy. Another possibility is that the accretion rate is too low. Jets might require a certain threshold of material, and Sagittarius A* isn't meeting it. Or perhaps there are jets, but they're weak, diffuse, and difficult to detect. The mystery remains, but it's a reminder that not all black holes behave the same way. Each one is unique. The balance that keeps Sagittarius a stable, despite its extreme environment. Sagittarius A* is stable. It's not growing rapidly. It's not producing jets, and it's not disrupting the galaxy. The balance that keeps Sagittarius A* stable is between accretion and feedback. The black hole accretes material, but it doesn't accrete much. Most of the gas is blown away by radiation pressure and magnetic winds, and the energy released, even though small, is enough to heat the surrounding gas. This feedback prevents large amounts of gas from falling in. It self-regulates. If the accretion rate increases, the energy output increases, and that heats more gas, reducing the accretion rate. The balance is stable, at least for now, and it's what keeps Sagittarius A* quiet. In the future, if the gas supply increases, the balance might shift. The black hole might wake up, and the Milky Way's center might become much more active. But for now, the balance holds. The future of the Milky Way's core. What's the future of Sagittarius A? Will it remain quiet, or will it wake up? The future of the Milky Way's core depends on the gas supply. Right now, There's not much gas in the immediate vicinity, but that could change. In about 4 to 5 billion years, the Milky Way will collide with the Andromeda Galaxy. The collision will disrupt both galaxies. Gas will be funneled toward the centers, and Sagittarius A will have a feast. The collision will also bring Andromeda's supermassive black hole close to Sagittarius A. Eventually, the two black holes will merge, creating an even more massive black hole, about 8 million solar masses, or more. That merger will release gravitational waves, ripples in space-time that will travel across the universe. The future is dramatic, but it's billions of years away. For now, Sagittarius A remains quiet, a sleeping giant at the heart of the Milky Way. The collision with Andromeda that awaits. The Milky Way and Andromeda are on a collision course. They're approaching each other at about 110 kilometers per second, and in 4 to 5 billion years, they'll collide. The collision with Andromeda that awaits will reshape both galaxies. Stars will pass by each other, rarely colliding, but the gas clouds will collide. They'll compress, heat up, and trigger massive bursts of star formation. The galactic centers will be disrupted, gas will be funneled inward, and the supermassive black holes will begin to interact. They'll orbit each other, losing energy through gravitational radiation, and eventually, they'll merge. The merger will create a single, more massive black hole, and it will be accompanied by a burst of gravitational waves, powerful enough to be detected across the universe. The collision is inevitable, and it will mark the end of the Milky Way as we know it, but also the beginning of something new, a larger elliptical galaxy, sometimes called Milky Way, the merger of two supermassive black holes. When the Milky Way and Andromeda merge, so will their black holes, Sagittarius A** and M31**. Andromeda's supermassive black hole will spiral toward each other. The merger of two supermassive black holes is one of the most energetic events in the universe. As the black holes orbit, they emit gravitational waves. These waves carry energy away, and the orbit shrinks. The black holes spiral closer and closer. Eventually, they merge, forming a single black hole. The merger happens quickly, in a fraction of a second, and it releases an enormous amount of energy, equivalent to several percent of the black hole's total mass. That energy goes into gravitational waves, ripples in space-time that spread outward at the speed of light. Future gravitational wave detectors might be able to observe this merger, even though it's billions of years in the future. The waves will travel across the universe, carrying information about the event and allowing astronomers to study black hole mergers in unprecedented detail. The galactic heart that will one day reignite. Sagittarius A** is quiet now, but it won't stay that way forever. When the Milky Way and Andromeda collide, gas will flood the galactic center, and the black hole will feed. The galactic heart that will one day reignite will shine brightly. It might become an active galactic nucleus, emitting powerful radiation, driving winds and jets, and lighting up the center of the merged galaxy. For a time, the black hole will be active, consuming gas, growing in mass, and releasing energy. But eventually, the gas will be exhausted or blown away, and the black hole will settle back into dormancy. This cycle of activity and quiescence is common in supermassive black holes. They feed when gas is available, and they sleep when it's not. Sagittarius A** has gone through this cycle before. The Fermi bubbles are evidence of past activity, and it will go through it again. The galactic heart beats irregularly, but it beats, and one day it will beat again. The reminder that darkness creates structure. Black holes are dark. They trap light. They're invisible by nature, and yet they create structure. They organize galaxies. They regulate star formation, and they shape the cosmos. The reminder that darkness creates structure is profound. We often think of light as creative and darkness as empty, but in the universe, darkness is active. Sagittarius A asterisk holds the Milky Way together. Its gravity anchors the galactic center. Its past activity shaped the distribution of gas, and its future activity will reshape the galaxy again. Darkness isn't absence, it's presence. Black holes are real. They're massive, and they're powerful. They bend space, they stop time, and they remind us that the universe is more than what we can see. Sometimes, the most important things are invisible, hidden in the shadows, waiting to be discovered. The center of everything, and the end of understanding. Sagittarius A asterisk is the center of our galaxy, the point around which everything orbits, the anchor, the heart, but it's also the end of understanding. Beyond the event horizon, our physics breaks down. The center of everything is also the edge of knowledge. We can observe Sagittarius A. We can measure it. We can image its shadow, but we can't see inside. We can't probe the singularity, and we can't know what happens at the very center. That's okay. Science doesn't require omniscience. It requires curiosity and the willingness to admit what we don't know. Sagittarius A is a reminder of both, a reminder of how much we've learned and how much remains to be discovered. It's the center of our galaxy, but it's also a doorway to new physics, new questions, and new mysteries. And that's what makes it so beautiful. The center of everything and the beginning of wonder.